Great. Thanks, everybody, for coming to the talk tonight. It's called
Space-Time Adventures on Novena. Introducing Balboa. I'm Andy Isaacson.
And I'm Star Simpson. First, a little bit about what this talk is about. In the beginning, we'll give a little overview about what Novena is, if this is the first you're catching that word. That's the open hardware laptop / dev board we used to work on this project. Next, an overview of what FPGAs are and why you might want to use one. Then a little summary of the tools that exist today for working with FPGAs. And then finally, our manifesto and an overview of the work we've done on this project to date. So beginning first, here's some background. This is a picture of Novena. It's very exciting if you're just tuning in on this project. It's a completely open hardware laptop. In fact, it just began shipping last week. In the very classic style of hardware as it once was, it ships with a complete booklet of all the associated schematics, so you can go on and know quite a lot about what you're doing with the hardware in this laptop. It has a lot of very powerful hardware, Gigi Ethernet, dual USB. You can see some of that here. You might recognize the connectors. And most importantly, it has an FPGA right there. So what is an FPGA? An FPGA is, well, the acronym stands for Field Programmable Gate Array. So coming from the concept of an array of transistor gates that you can reprogram after it's been manufactured to take any arrangement you like. Importantly, it's a programmable circuit, so it's a really interesting combination of both software and hardware in that way, which you can use to implement any algorithm you can imagine. They're used, in short, to solve any computable problem. And any computable problem is a given that you can implement, say, a complete CPU to solve any computable problem that way. Why they're better, why you'd want to use one, is they're often faster at solving specific problems, especially problems that can be computed in a highly parallel way, or in a way that's more gate efficient when you use a dedicated processor for it. So next, a couple of definitions, some terms. These are some words that you'll want to know when you begin working with FPGAs. You'll hear the first term, LUTs, a lot, and it stands for a lookup table. So I'm going to skim the surface of the hardware side of this talk about as close as we're going to get in discussing this. If anyone here recalls early electrical engineering explorations, logic gates, you have AND, OR, so forth. Those are basically two-input lookup tables themselves. You have two inputs, and you get something as a result of what those inputs are. In an FPGA, you have this concept sort of taken well beyond to the next level. So instead of just two inputs, commonly today in Xilinx FPGAs, you'll have 6, and the outputs aren't defined in terms of like standard canonical logic. It's anything that you want it to be. So any input, you can define every output in combinations of 6. So that's the smallest unit of computational cell you'll discuss in terms of FPGAs. Larger sizes from there, logic cells will be your groups of LUTs, along with some flip-flops and multiplexers. Those are the things that you set that determine how your FPGA will go about doing its computation. Bigger than that, logic slices are blocks of 2 cells, or a couple of cells in combination. Logic blocks are a couple of slices, maybe 4. And then zooming out even further, you have the FPGA fabric, and that's discussed fairly often. The fabric is, you can imagine that these logic blocks are sort of floating around in a sea or mesh, which you also program the connections between, and the fabric is that physical layer that those blocks are floating in. And finally, core is the overall definition of how the gates will all be assembled. And going on a little bit more, so you have this FPGA. So how do you go about programming it? FPGAs are programmed in what are called hardware description languages, HDLs, which is a human-readable source code language similar to C or other system programming languages. It's similar to other programming languages you'll be familiar with in that it has a toolchain, which is much like a compiler, and it turns your code into a final bit stream, which is analogous for our purposes to an executable. And that bit stream actually switches the physical connections and describes the physical interconnects inside your chip. Here's an example of an HDL. This is Verilog. It's one of a couple HDLs. It's the one we actually chose for writing our projects in. In fact, Easter egg, this is actually code we wrote for the earlier project, which became this project. This is part of the AES encryption algorithm doing computation. If you're familiar with Verilog, you've already read it.
And if you're familiar with Verilog, you might be able to find the bug in this code.
One thing that's interesting about this is if you're familiar with Python or C, you'll notice that that beginning line, the module subbytes, that looks like a series of arguments, but in fact, those are actual physical inputs here. Those are thought of as wires that connect it to other things.
Or output wires.
You will see more of those, I suppose. And so if you're interested in learning more about Verilog, we worked through this book and found it very useful. Just a little shout out to Verilog by example for those of you looking to go from here and learn more. As a counterpoint, felt it prudent to include this VHDL example. In evaluating our HDL, we decided we liked Verilog a lot more, but for the sake of completeness, here's what VHDL looks like. VHDL, just one of many HDLs. Those terms are not interchangeable. So you write all this code. How do you go about building for the FPGA? What's the process like? It's analogous to compiling, but exists in several different concrete parts. So the first part is synthesis. And during synthesis, your definition of what you want your circuits to do is converted to a list of internal connections. And the output of that is called your netlist. Then it moves to a stage called place and route. And I think this is where it gets interesting for me from the electrical engineering perspective, because FPGAs are fundamentally two-dimensional. And in order to implement the algorithm you want to compute, you have to actually physically lay it out inside this chip. And it's similar, I think, to urban planning in some ways, in that you might have two different modules that you need to be in communication with each other. And if you do this part wrong and run a connection straight between them, they will never be able to communicate. It's also called mapping by some vendors. So the geometric aspect of this is certainly very important. And then subsequent to that, you have the bitstream generation stage, where you take your physical layout and your connections and turn it into that file with the switches that turn the chip into what it should be. It's worth noting that bitstream generation seems like it'd be fairly straightforward, but is highly vendor specific. The tools for doing that are fairly proprietary, but as a note, there's some very interesting reverse engineering efforts here to understand and publicly document those systems. Find out more on the internet.
So Star described a lot of the hardware of the FPGA, and the last part in sort of the system diagram is this idea of an FPGA core. So what is an FPGA core? To be very concrete about it, the core is just a chunk of source code which does something, which implements some process or algorithm. It's probably written in Verilog, VHDL, or possibly in some higher level, more abstract hardware description language, which gets turned into Verilog or VHDL on its way into being in the chip. There's one really interesting distinction in the FPGA world between a soft core versus a hard core. And FPGAs have, over the years, evolved such that the vendors realized many people are spending a lot of their space in the FPGA doing some specific things. So let's just go ahead and put that down on the chip as hardwired, and that's a hard core. And then if you're implementing something using the hardware description language in Verilog or VHDL, that's a soft core. It's software. Now, many people in this industry, when they say core, what they mean is IP core. And IP here is intellectual property core. So this is the idea that this source code is owned by someone, and they have the right to sell it, to sell that idea, to market it to others. And they can be exclusionary about that, not share it with people they don't want to. So IP here is intellectual property, not internet protocol, which is what I kind of was hoping when I first saw the phrase IP core. But alas. So it's interesting because this FPGA world, like the community of people who develop for FPGAs, are almost, I would say, mentally poisoned by this term. The fact that the thing that you're building is a core, and well, a core is just an IP core, that means that I own it. That means that everything that is built is owned by someone. I don't think that's how it has to work, and that's one thing that we were really excited about in this project when we realized that OpenCores exists. So OpenCores is a website, opencores.org, and a project and a philosophy to build freely licensed cores for FPGAs. Amazing project. They've got hundreds of cores, hundreds of different designs. You can customize them, you can integrate them. They have a shared bus interface for many of these. So they work together really well. It's really an amazing example of the free software philosophy in action. So OpenCores is cool, and IP cores are less cool, but there's an important concept there. But in the Balboa project, we use the word core a little bit differently, and we'll talk a lot about accelerator cores, and what that exactly is I'll get into in a little bit. But I wanted to put a pin in that here so that everybody's on the same page.
So next we'll discuss a little bit more about the environment that this project exists within. From the hardware to the software that currently exists to support FPGA development. So here again is Novena. And this slide exists to give you a sense of how FPGAs are measured, sort of. You can see that this has 43,000 logic cells. That makes it about a medium-sized FPGA in the Spartan 6 family. It's got, two different kinds of RAM here. And then actually, the second to last line item here is interesting. It's got a hardcore, which is a DSP, that DSP48A, a digital signal processor, built into it. Just as Andy was describing, they've chosen to include that here so that it's permanently available. It gives you a bunch of things. You get an 18 by 18 multiplier, an adder, an accumulator, and you don't have to write those things for yourself. They're there. A little bit more zoomed out on the Novena laptop itself. The FPGA is directly connected to the ARM processor via a very fast bus, 16 bits, and we will use that more. And, we've been asked in the course of preparing this talk, that's great and everything, but, why is there an FPGA on Novena? What would I want to do with it? And these are not things you might necessarily even want to do with it, but these are things you could want to do with it. So you could, you could have fun and attempt to put some Bitcoin mining into action. You could emulate another processor with it, so you could have that ARM talking to a softcore processor of some other kind. You can use it for crypto. As I alluded to earlier, our first project was to implement AES. Our goal then was to accelerate SSL computations on the CPU. You can do co-processing. And you can also use it for processing over, data you might be acquiring. Actually, the Novena's pretty great. It's got this amazing analog to digital converter, which lets you get in.
Star, I'm in software. Is 500 megasamples per second actually awesome?
Tell me what you think, Shane. I hope it's fast enough for you. It's also great for doing, the Novena has additional boards, for example, a software-defined radio. You might use it for video or image processing, things of that sort. So now a little bit about the ecosystem of open source tools that you could use for targeting the FPGA for building your course. A shout out to the creators and maintainers of all of these projects. First, this is Yosis. Yosis is something we're actually extremely excited about. It exists not in the same space as Balboa, but in a very complementary space. It strives to be what I think the proprietary tools that you can get today, like Xilinx, ISE, and so forth, to do that, but in a free way. It is not a complete replacement to date. It can get you through synthesis. It has the start of place and route system, and it doesn't do bitstream generation. But we're hopeful that with a couple of Xilinx extensions, Yosis could get there. It's also worth noting that this project has existed for about, I think, only 2 years, and I think has been sort of worked on by like one guy so far. So it's pretty amazing how far it's come. It's open source. It has a Verilog toolchain, and also outputs to any ASIC or FPGA backend. Next, a quick word about MyGen. If you attended previous CCCs, you might be familiar with this board called the Milky Mist. I like the Milky Mist a lot because its sole purpose in life was to do really beautiful video generation using an FPGA. And the team that worked on that produced a lot of useful software as well, including this, which is a Python toolbox for building hardware. It lets you write a high-level description of your circuit in Python, and then outputs Verilog or VHDL. It's also used in actual projects, which is a strong plus. We just thought we'd include a little example of what the code looks like for this and the following 3 examples, so you can sort of get a sense for what it would be like. It's a basic MyGen example. MyHDL is a project that I like a whole lot. We ended up writing directly in Verilog, but we considered writing in MyHDL. It is, rather than being a toolbox for targeting hardware, it is you're actually designing hardware with Python. It has a lot of docs. Their website is really good, and I really liked what the developers of this project put into their website to support people who would want to use it to program their hardware. It is sort of like just a Python syntax for Verilog, and it also runs and gives either Verilog or VHDL, your choice. So here's a snippet of a MyHDL project. One thing I really like about this example is it's in a very well documented style. All of their documentation is like this. And finally, Chisel. Chisel is very different from the previous 2 examples. It strives to let you design hardware embedded in Scala code. It's often one-to-one with Verilog that you'd be writing. But their philosophy is very different, and their philosophy is really what's most interesting. It's actually produced by a UC Berkeley group led by Jonathan Bachrach. And one thing that's really interesting is that RISC-V, which is a new, completely open CPU, was written entirely in Chisel. So that's pretty cool. There's a paper associated with Chisel that's pretty great. which goes into further depth about the tension between having a general purpose hardware description language versus having a domain-specific language for describing your hardware. And here's an example of that Scala code describing hardware. Great. So you might ask, like, why we need a free toolchain, like other than free software, is great, raw. One problem is that a lot of the proprietary tools are sort of monolithic and they seem a little creaky. And our hope is that a free FPGA toolchain would not only let you flexibly target any FPGA you might be working with, it'll also lay the groundwork for new hardware description language experiments, which I think is part of what Chisel's getting at in their paper about the tension between current monolithic HDLs. Faster builds. Targeting FPGAs today is notoriously takes a long time. Our fastest Xilinx ISE builds were about 40 seconds, which is all day. It's enough time to go get a new cup of coffee, and you can only drink so much coffee. And then finally, longevity. The idea here is that free software has a greater lifespan than any proprietary software. Vendors come and go. You don't want to be locked in. GCC's been around for a really long time. We think something like that could exist.
So we promised you space-time adventures. So here's the space-time picture from Wikipedia. Like Wikipedia a lot. In order to get into the space-time adventures, we have to set the stage a little bit. Roll back and look at the history. Let's go back to 1965, 1970. Computers existed. Everyone had read a newspaper article about computers. But how did a computer come to solve an actual problem in 1965? Well, you had this computer with a CPU, and you have a team of programmers who are going to build an application for this computer. That CPU, that's computer hardware, that application, are going to exist together. There's going to be a fixed thing which exists at the end of this project, which is solving that problem, whatever that problem is. Maybe it's a banking application. So this bank is going to have this computer, and it's going to be their computer. So you have the CPU, and you have the team of programmers, and maybe the team of programmers realizes that the CPU doesn't quite do what they want. So they ask, well, let's just change the CPU. Let's add an instruction to it. So now the CPU gains the ability to do a binary coded decimal, because that's what they were going to do in this banking application. And the team of application programmers are building for this computer. So they write in, of course, in the assembly language for this computer, for this CPU, with its new custom instruction. And that application is obviously only going to run on this computer, the one in Poughkeepsie. You wouldn't necessarily think of also running it on the computer in Minneapolis. So that application and that computer are bound together. And the peripherals as well. The printer gets wired into that computer. The computer is modified to talk to the peripheral. So now you have a printer and maybe a tape drive attached. And now you have this object which has been created, which solves this problem. It's really cool. It solves the problem. This was really cool, especially at the time. But it's monolithic. It does exactly one thing. So rolling forward a little bit, 1972. 1972 is the year that Unix was released in a portable form. A new operating system, not the first operating system, not the first operating system to provide the features that it provided. But I would argue at this point, clearly the most successful, long-lived, really groundbreaking operating system. Unix brought in amazing innovations for software modularity. Unix really popularized multitasking, so you could have multiple programs running on a single CPU. This was kind of crazy in 1972. Why would you do that? How could you do that in a way that actually works? Unix also introduced virtual memory. You no longer had to map the physical addresses directly and program your overlays so that your code would fit on the machine. And kind of most revolutionary, Unix was programmed in a high-level language, or at least what was considered high-level at the time, programming language C. So this is just amazing. I mean, it's hard looking back today to imagine how amazing it was that this underlying technology enabled component reusability for software development. I mean, wow. Such computer. So we gained a ton of infrastructure as software developers, and it was a really long, drawn-out, painful process. Not everyone got it at the beginning. The idea that reusability, small components, pieces working together in the service of the goals of the final user of the computer would actually be a good thing. And some of these technologies today are so taken for granted that it's hard to even remember that they exist as discrete, controversial at the time technologies. Virtual memory, very controversial. I started my career at Cray, the supercomputer company, and I had coworkers who remembered this battle. Now, virtual memory is a fad. It's never going to take off. Time sharing, the fact that you could have multiple users using the same CPU simultaneously, I mean, looks good in a research paper, but who's actually going to deploy that in production? Operating systems with these APIs, like you can just call things and things happen in a semi-reliable manner, and you get bug fixes, and your application just keeps calling the same function and it works better. How does it even happen? Networking, I just call socket and TCP does a bunch of packets under the hood, and it's amazing. Device drivers, that TCP layer isn't talking directly to the Ethernet card, it's going through several layers of abstraction. We write all of these tools that we're building these days in high-level languages, and they all rest on the foundation of compilers that turn our expressive thoughts into discrete actions on the hardware. And we have libraries. We have these vast libraries of software. Some of it's really terrible. Some of it's better. Some of it's very new and won't last for very long. And other parts of it are like LinPack, and we're still running code that was written in 1973. It's amazing when you think about it, how all this infrastructure has really separated us from where we were at the beginning of the computer revolution. In conclusion, I can wrap it up and say that we don't program to bare metal anymore. We've managed to move up layers of abstraction and have gotten a lot of capability as a result.
So now, given that background, it's time to tell you the manifesto of our project. Our vision is to let us do more than one thing at a time on the FPGA, and to do so flexibly.
Or in other words, writing and using an FPGA accelerator core can and should be as easy as writing a high-performance C application. I actually expected laughter rather than applause there because
I blame our test audience.
Because as those of you in the audience who've done this know, writing a high-performance C application is no easy matter. But imagine trying to do that in assembly. It would be a lot more work. So I wanted to emphasize that the goal of the Balboa project is to build dynamic, reconfigurable computing. And each of those words matters. It's dynamic because what the hardware is doing at any specific time can be changed with the flip of a switch. It's reconfigurable because what you've expressed as the accelerator core can be moved around the FPGA to optimize resources or to allow room for another accelerator core to be loaded. And it's computing because Balboa is focused on the idea of enabling computational acceleration on FPGAs. FPGAs are also amazing because they have fantastic I/O capabilities. They have really fast digital I/O, really fast analog I/O. Those are awesome. Those are fantastic. I'm glad they exist. I totally use things that have FPGAs in them, but that's not what the Balboa project is about. It's not the killer app for me. So Balboa is getting down to the actual nuts and bolts of the system that we've built and that we're planning to build. Balboa is a library and some control software which runs on the CPU of the Novena platform. And the control software makes sure that the FPGA is doing its job and that the apps are able to access it correctly. And Balboa is also a bus and management layer on the FPGA implemented in Verilog, which you can plug into, you as a developer of a accelerator core can plug into when you're writing the core. And we hope that it will provide infrastructure and useful management so that this job becomes a lot easier. The Novena hardware platform looks a lot like this in block diagram, leaving out some of the complicated bits. We're a little bit further in than we were in the last slide that had this picture on it. The FPGA and the ARM CPU are connected by that fast bus. Both the FPGA and the ARM have their own DRAM associated with them. The ARM CPU has the standard complement of interfaces, USB, Gigabit Ethernet, HDMI, and so on. The FPGA also has I/O up at the top for those times when you just have to get out into the outside world. And now diving in to see how the software maps onto this physical architecture. We've got the Balboa system here. In the FPGA world, we have the Balboa bus, which provides the management and the interconnect. We have many different cores running on the FPGA simultaneously. And then on the software side, the interface is mediated by libbalboa. And talking to libbalboa, we have the management software, FPGA daemon, and any apps that are trying to use the FPGA cores, accelerator cores, to compute their favorite function. So the Novena laptop is amazing. It has this really quite large FPGA. I say huge here, and I should quantify that. There's enough room on the Novena FPGA to have 2 full 32-bit CPUs running simultaneously with plenty of room to spare. So there's a huge unexplored territory here of things that could be done with the FPGA. And it's time to go exploring. And it's a brave new world. So here's the vision, where we can go, and why having Balboa will be cool, and is pretty cool already. Balboa provides interoperability of the accelerator cores. So you can use multiple cores simultaneously on a single FPGA. And it also, we're hoping that that the tooling will improve over time. Currently, we're using the vendor toolchain, and it's not great, although it's getting better as we figure it out and learn the ins and outs. FPGAs currently aren't as useful as they could be. Many Novena users don't have any plans to use their FPGA because they don't understand what it could possibly be useful for. So we think that with some infrastructure, the Balboa infrastructure, the FPGA on the Novena will be a lot more useful. Now, one point that it took me a while to get to here is that the point of Balboa is not building the tools and the compilers. The point of Balboa is really to allow us to use the FPGA efficiently with less overhead of doing so. It doesn't matter to me if my FPGA can run something really fast if it's a lot of work for me to set up. I can't even begin to tell you how many cool FPGA boards I have that I bought because FPGAs are cool and they're sitting in my closet because they're too much work to set up. The point of Balboa is to let us do more than one thing at a time on the FPGA and to do that flexibly. So the goals of the Balboa project is that you, developers, write cores in your chosen HDL. Currently, I would recommend Verilog because the alternatives aren't completely baked, but I can see paths to a better future. You get fast, direct access to the core. libbalboa just sets things up and then gets out of the way. You get standard interfaces for both the core and the application. I spent several months at the beginning of this AES project trying to figure out how the heck I was supposed to connect the Verilog that I was writing to the software that I wanted it to talk to. And most importantly to me is that with Balboa, the end user chooses what runs and when, drawing a connection back to how software reconfigurability completely changed the world. Today, no one would think of having a single-purpose computer that costs an enormous amount of money and only does one thing. The person who's using the computer chooses what it's doing. And with Balboa, we can do the same for FPGAs. The authors of accelerator cores and the authors of applications that use them can build something, can build some components in the Unix philosophy, build something small that does one thing well. And the end user gets to decide when and where that runs and what it does, taking it places that the original author never could have dreamed of. So, how far along on this ambitious vision are we today? Frankly, after we started this project most of a year ago, we're not as far along as I had hoped I would be at Congress this year. But we have some really encouraging results. We do have multiple cores running on the FPGA, one at a time. So we can bring up one core, run with it for a while, and then say, I'm done with this. I'm going to start a different core and start that. And the Novena system continues running flawlessly. Apps using the Balboa system can mmap the core and get direct access to the registers exposed by the accelerator core. And we're doing this all currently without a kernel driver. I'm not sure that we can keep this up. I think that a kernel driver is going to be a critical part of the system in the medium to long term. But for now, everything can be done from a userland process running as root. YOLO. So that's the current status of the Balboa project.
So at this point, we're going to discuss what's coming up next for us on the Balboa project and what we'd like to see happen. So first, 7 security issues.
Yeah, so the introduction of time sharing and virtual memory, in addition to enabling enormous kinds of productivity and creativity, also brought in some security challenges. Now you have resource exhaustion issues. You can DOS a computer because there are multiple things running, and maybe one of them is trying to prevent another one from running. Many similar kinds of problems can happen.
What should we call this?
What should we call this? 7 security issues. I don't know, they're challenges, things that could happen on an FPGA if you're doing it.
Or 7 awesome hacks.
So 7 ideas for potential security problems or awesome hacks, which I hope someone at a future Congress will present on. The first one electromagnetic coupling. There's this amazing paper by Adrian Thompson from 1996 called An Evolved Circuit. The full title is actually a little poem, but it didn't fit on our slide. The picture here is a picture of the circuit which he evolved. And there's some gray, oh, they're completely unreadable.
Unfortunately, they're not visible.
Yeah, there's some gray squares up there, around the edges of that circuit. They're not connected. And according to the documentation of the FPGA, unconnected functional blocks shouldn't be able to affect the outcome of the circuit at all. Shouldn't be able to, according to the documentation. Turns out that if you remove any of those functional blocks from the design, the circuit stops working. The documentation isn't telling me the complete truth? I'm shocked. An interesting side note here. So this paper is amazing. I recommend that everyone read it. It was on the web for like 15 years. It's totally incredible paper. Really well done with some high quality 1996 web design. It's great. And the University of Sussex restructured the website in 2013. And now that paper is no longer on their website. The links on Google go nowhere. Adrian's paper is only available on archive.org. So a shout out to the Internet Archive. Even the academics are trying to delete the web.
It's important for us because cores have never really been shared on the same FPGA before. So the question this raises is whether you could create an appropriate antenna in hardware to snoop on other processes being computed on the same FPGA.
Seems like it should be possible. Documentation says it won't work, but second awesome hack. That bit stream that is output from the toolchain and then fed to the FPGA over a hardware interface. It's a stream of bits. It's a language. In the hashtag, it's called langsec, the idea of tweaking inputs to a given interpreter to find unexpected behavior in that interpreter. The FPGA bit stream is a language with an interpreter implemented in hardware in the FPGA fabric. What happens if you give that interpreter unexpected input? Do we get weird results? I bet we do. It's only gotten trusted inputs so far. Which leads to the second option, bitstream exploits. In our pre-talk prep, we talked to someone who's actually done some reverse engineering in this space, Zobs, and he pointed out that the bitstream apparently can fairly easily be configured to connect power directly to ground. And everyone who laughed has let out the magic smoke at some point by doing exactly that. Probably some really interesting, fairly expensive experiments that need to be run there.
You too can talk to Zobs. The Novena hardware forums are very good.
It's true. The bus protocol. The FPGA on the Novena and the CPU on the Novena are connected with this EIM bus. Some acronym, doesn't matter what it says, it's a bus. It's pretty complicated because it has a very sophisticated protocol with very strict timing requirements. So when the CPU asks the FPGA for a given memory address, the FPGA has a responsibility to return an answer within a certain number of clock cycles. And if the FPGA doesn't return, the CPU might crash, might hang, ask me how I know, ask me how many times I power cycled my dev hardware. Either the core, the accelerator core on the FPGA, or the app might be able to trigger this. So there's some really interesting fuzzing work to be done. Hopefully we can't light things on fire as easily at that part of the protocol. That leads into the fifth awesome hack, malicious apps. Once I have an app with access to an FPGA accelerator core, it's talking over that EIM bus to the Balboa bus on the FPGA. What can the app do to trigger unexpected behavior? Now, most things are pretty robust. I'm sure that if you do normal things from your app, then nothing bad will happen. But what happens if the app issues an unaligned read to the FPGA? Maybe it works right. Maybe we see some really interesting behavior. Had a joke there, but I've lost it. Another awesome hack, timing attacks. One of the reasons that FPGAs are so cool is that you get down to the cycle, the clock cycle, 50 megahertz or 100 megahertz or 200 megahertz, accurate timing information. When something happens, you can know exactly when it happened. Sounds like a great way to build a timing attack on a software algorithm. If I can extract the exact cycle when some I/O happened, I can probably find out some really interesting things about your cache misses, the layout of your AES key table, your RSA implementation. Should be a lot of fun. And the seventh awesome hack is hardware backdoors. Now, there's this interesting idea that some people have bandied about for why we should switch to FPGAs. And to make this make any sense, I have to put on my paranoid tinfoil hat and say, you know, I'm worried that the NSA might have put a back door in my Intel CPU's AES instructions. And I'm going to fix this by not using an Intel CPU to do my critical, secure computation. Instead, I'm going to use
our slides look fine here, so.
The NSA had nothing to do with that, I'm sure.
I'm not so sure.
So I'm going to use a soft CPU. It's written in Verilog. I can look at it, read the source code, and convince myself that it's correct. And I can look at the bit stream and convince myself that it's correct too. The NSA have not backdoored my tool chain. And I'm running on an FPGA, which is just a sea of gates. So everything should be fine, right? I can trust that they didn't backdoor every gate on this FPGA. It turns out the urban planning metaphor was very accurate. You can't just put the parts of your soft CPU anywhere on the FPGA fabric. If you have an FPGA, the ALU and any AES accelerators that you put are going to end up in a fairly small set of places on that fabric. So if I am the NSA and I'm in charge of backdooring an FPGA so that it will be able to snoop on the AES keys of a soft CPU implemented on that FPGA, I can probably manage to do it, turns out. Sad face. The backdoors, in short, the backdoors will probably still work, if they exist at all, which they don't, because I took off my tinfoil hat.
And our slides are back, so that's good. As far as the rest of Balboa goes, we could use your help. We'd love to have people join our project. And we're going to wrap up by describing 7 things that we would like to have help working on.
So our current proof of concept is just one core at a time. We can build the accelerator core and synthesize it and load it onto the FPGA. But as a next step, one goal of the project is to make it really easy to take multiple cores, synthesize them into a single fixed bit stream, and load that onto the FPGA. Pretty straightforward how to do it. A little bit more code to write. Could use some help. Dynamic reconfiguration of FPGAs is a really interesting area. Now, most people who are using FPGAs reconfigure the whole thing at once. You configure it once at boot up time, and now your FPGA is a software-defined radio. And you, if you need to do something else with it, if you want to use it as a Bitcoin miner, you stop using it as a software-defined radio and load the Bitcoin mining bitstream, and now it's a Bitcoin miner. Well, it would be really cool if I could have the software-defined radio taking up 2/3 of the FPGA and dynamically decide, oh, I'd like to do some Bitcoin mining, load the Bitcoin core on the remaining space, and go from there. and then decide, oh, I need to do some secure, I need to do lots of crypto, so I'm going to unload my Bitcoin mining rig and load up a crypto accelerator without stopping the SDR. This is theoretically possible. The documentation says that it should work. Haven't gotten it working yet. Having multiple cores on the FPGA, running on the FPGA simultaneously, using the bus between the FPGA and the CPU in a fair manner. So we need bus arbitration. And related to that, allowing multiple apps to use the FPGA bus simultaneously will require some software work on the Unix side, on the Linux side, to let the mmap mappings interoperate cleanly. The Balboa FPGA, the Novena FPGA has a bunch of really cool I/O, and we should be able to use that. That's just a matter of teaching the Balboa framework about those resources and giving it a management layer. And related to that, using the RAM, that RAM that's attached to the FPGA. Currently, if you wanted to use that in a Balboa core, you would have to do a bunch of hand coding in Verilog. That should be easier. There's no reason for it to be as complicated as it is. And the last, and perhaps I think the most important, is that we should be able to implement cores for Balboa using higher level languages, not having to write Verilog ourselves, because writing Verilog is kind of a pain.
So here's how you join. I will admit that when we found out our talk was accepted, we hastily whipped up a wiki, etc. You can join the conversation on Twitter with our cool hashtag. And we hope to see you join. Finally, I will say that the Balboa FPGA GitHub is of special note. Clone away, check it out. We'd love your feedback. To date, the best way to get in touch is via Twitter, which we'll use to bootstrap to email. Thank you so much. Special thanks to everyone who helps us with this project. And the creators of Novena are, in fact, in the room. It's very exciting. And we hope to spur a huge amount of work and excitement on this project. So thank you.
Okay, thank you very much. We still have some minutes left, not too many, but we have some minutes left for questions. So as usual, please line up behind the microphones in the room. And I think the first question goes to you.
So, Star, one thing that we never explained in our talk is the name, Balboa. Where does that name come from?
Andy wants me to answer where the name Balboa comes from. I don't know if you all read Bunny's blog as closely as I do, but we learned that Novena, the name of the laptop, is in fact the name of a Singaporean MRT station, somewhere apparently close to where Bunny lives. We just thought we'd shoot one back. Balboa is, we think, the equivalent BART stop in San Francisco. So whenever you're passing through Balboa Park Station, little nod.
Think of FPGAs.
Okay, first question from here in the front, please.
Yes, about I have a question about the numbers. In the earlier slide, you said Novena features an ADC with 2 times 500 megasamples per second, 8-bit. So that's 1 gigabyte per second. How much of this bandwidth is available over the Bilbao interface between the FPGA and the ARM?
The question is, how much
bandwidth is available between the FPGA and the ARM core?
Between the FPGA and the ARM.
Between the FPGA and the ARM.
So the FPGA on Novena suffers. I'm not an expert in this area, but I can address the question. The question is, we have a lot of samples coming in to the ADC converter, analog to digital converter, and only a smaller amount of bandwidth available to the CPU. What you end up doing in a case where you're doing something like that is doing some kind of downsampling or processing in the FPGA to reduce the samples to a rate that the CPU can accept. And there's a lot of work. That's one of the primary things that software-defined radios do on FPGAs. So for that kind of thing, SDR experts are the people to talk to.
Okay, you can build a digital down converter and a numerical oscillator in the FPGA and then build a software-defined radio.
Exactly.
Yeah.
Okay, can I please remind everybody that we're still in Q&A, so please keep the volume down, and please, if you have to leave, do it quietly, please. Otherwise, we can't hear anything.
Next question.
Yeah, please a question from the front, from the other side.
This is really cool and exciting. What kind of applications do you think would be most suited in terms of, I don't know, performance per watt or peak performance, and how would it compare to GPU acceleration in terms of what you can do with it?
So GPU acceleration, the question is GPU acceleration versus FPGA acceleration. What applications are well suited for FPGAs? The one thing that springs immediately to mind is anything where the timing matters a lot. So we started out with this project doing AES GCM because it turns out that the GCM mode of AES requires hardware support in order to be secure. You can write software that does GCM, but it will nearly inevitably have a timing information leak. With hardware, you can avoid the timing information leak. So there's a case where it matters a lot.
Another answer would be I'm personally very excited about the potential additional uses of Novena as an oscilloscope. And just off the cuff, I can imagine a project where you're sampling a high-speed circuit and you have some action that the FPGA takes by sampling that and outputting. I know Andy lives in an I/O devoid world, but that would be something I would think was pretty cool. Next question.
When swapping out cores, is the state fully preserved, or do you have to
Sorry,
I can't.
we can't hear you. Could you speak a little closer to the microphone?
Very close to the mic.
when you're swapping out cores, is the state fully preserved, or do you have to continue from a safe state?
When you're switching between cores,
Yes, when you're switching back to one you used before.
Yeah. Excellent question.
is state preserved or do you restart in a new state, was the question.
Exactly. I don't want to answer incorrectly here, so I'm taking a second. When switching between cores, if the core has state in its FPGA circuit, that state needs to be preserved when you swap back, or else you can preserve state at a higher level where the application, or rather the library, the Balboa library, preserves the transaction before it's sent to the FPGA, so that when it's swapped back in, you can restart that calculation.
One good way to define the future is to help us write it. Next question.
Hey, thanks for giving the talk and the nice project, really.
Thank you.
Although I've backed the Novena project, I'm wondering how heavily tied is the Balboa architecture to the way, how tied is the Novena, the Balboa project to the way that the Novena has the FPGA attached to the processor? How portable is it to other pieces of hardware?
So our goal is to be able to, the question is how heavily tied is Balboa to Novena in specific? And our answer, I think, is that our goal is to target any FPGA. Ultimately, at present, we're using Novena as a dev board platform to get started.
You need somewhere, that's exactly right, and I'll expand on it by saying that you need somewhere to run the software component of this. That doesn't have to be an ARM CPU attached to an EIM bus. One of the goals of having the abstraction layer is that you could have different interconnects, and I hope that someone will make a computer I can actually afford which has an FPGA on the hypertransport directly attached to an Opteron or similar computer. Cray actually makes a supercomputer like this. They started like $10 million.
In the interim, an interesting project you might want to look at is the Zinc FPGA platform, which has a hardcore CPU on board for very high-speed throughput between the FPGA part and the CPU part.
And
it's another possible starting point.
That's a great next step. And the last next step is that I really want to see the Balboa architecture or something like it running on a soft CPU that's running on the FPGA while reconfiguring its own FPGA. And if we can...
Yo, dog. Thank you.
Sorry, I have to cut you short here because we run out of time and the next talk is going to be really crowded.
We want to answer all your questions. We'll be outside.
All right, so all people that are having still questions, please go with them outside. And again, I ask you for a warm round of applause. Thank you very much.
One last request. Could someone please make a free Twitter replacement so I can stop using Twitter as my primary means of talking to people about stuff like this?